Hello everyone and welcome back to Introduction to Number Theory. We're dealing with quadratic remainders, and in this video I would like to discuss the Eulers Criterion. First, notice that if A is a quadratic remainder, well we can write that A is equal to B squared, but we assume that A is congruent to B squared modulo P, where P is a prime number. Then A to the power P minus 1 over 2 is congruent to B to the power P minus 1, since A is like B squared. And this is congruent to 1 according to Fermat's small theorem. So, for every quadratic remainder A, we see that A to the power P minus 1 over 2 is congruent to 1. And what if A is not a quadratic remainder? So, it is not congruent to B squared modulo P for any B. Then, in this case, it appears that A to the power P minus 1 over 2 is congruent, modulo P, to minus 1. And this is Euler's criterion, which says that if you wish to check whether A is a quadratic remainder or not, then you need to raise it to the power P minus 1 over 2, and you will get either 1 or minus 1 modulo P. And in the first case, it will be a quadratic remainder, and in the second case, it will not be a quadratic remainder. Of course, in all this, we assume that A is non-zero. Let me just write it down. Non-zero modulo P. Well, because 0 raised to any power will be 0. There are several questions here. Well, first of all, why minus 1? Why not some other remainder modulo P? Recall the Fermat small theorem, which states that A to the power P minus 1 is congruent to 1 modulo P, which is equivalent to the fact that A to the power P minus 1 minus 1 is divisible by P. And since P is a prime number, and we assume that it's greater than 2, because P equal to 2 is not an interesting case, then P is odd and P minus 1 is even. So we can transform the left-hand side into such an expression, P minus 1 over 2 minus 1, and A to the power P minus 1 over 2 plus 1. And this is divisible by P. So once again, P is a prime number, which means that one of these expressions, one of these brackets, must be divisible by P. Well, in case this one is divisible by P, we can say that A to the power P minus 1 over 2 is congruent to 1 modulo P. And in case this expression is divisible by P, then we can say that A to the power P minus 1 over 2 is congruent to minus 1 over P. So we see that for every A, of course, non-zero modulo P, raised to the power P minus 1 over 2, it will get congruent to either 1 or minus 1 modulo P. So now going back to the statement of Euler's criterion, we understand that, okay, so for every A raised to the power P minus 1 over 2, it will be congruent to either 1 or minus 1. If we take a quadratic remainder, we will get 1. But why do we get minus 1 in case A is not a quadratic remainder? Recall that we know the exact number, the exact amount of quadratic remainders modulo p. If we exclude 0, then there are exactly p minus 1 quadratic remainders. Let's write this down. So p minus 1 over 2, of course, p minus 1 remainders in general, and p minus 1 over 2 quadratic remainders. And consider a polynomial x to the power p minus 1 over 2 minus 1. And it says here that every quadratic remainder is the zero of this polynomial. However, there are exactly p minus 1 over 2 quadratic remainders. And the very same number is equal to the degree of this polynomial. The degree of this polynomial is equal to the number of quadratic remainders, and every quadratic remainder is a zero of this polynomial. Well, this means, recall that a polynomial cannot have more zeros than its degree. This means that quadratic remainders form the total set of all zeros of this polynomial. So no other remainder modulo p can be a zero of this polynomial. Therefore, non-quadratic remainders have nothing left but to be congruent to minus 1 when raised to the power p minus 1 over 2. And this finishes the proof of Euler's criterion.